Let's say you work for a company and your manager is mad that there are pirated versions of your product out there. He tells you to secure their intellectual property and make the program uncrackable. Is that even possible? Last video I claimed that every program is crackable. But that was old me, maybe I learned more in the meantime, so let's try it out. First problem is that the license key was inside the binary. The simple technique we had was to extract all strings and we found the key. Our first attempt to make it secure would be not to have the key inside. We can do this by writing an algorithm that scrambles the key. You can come up with very creative ideas and then you can give the secured binary to your friend and ask them to crack it, or write a Keygen. That can be really fun. The first idea I have is to simply sum up the ASCII values of the key and compare it to a magic value. So let's modify the original program. First we have to define a new integer value that will store our calculated sum. So int sum and set it to 0. Then we will add a for loop with the counter variable I, which starts at 0, with the loop condition that it continues to repeat this loop as long as I is smaller than the string length of the key that we can supply with argv1. And in each repetition we will increment I by 1. Now we want to sum up the value of each character. So sum plus equal argv1 and then the index I. As you know, a computer understands only numbers, so each character, as you know from the ASCII table, is a number. But the compiler knows that argv is defined as a character sequence. So to not get any complaints, we cast this value to an integer, like that. Now we want to find out what the sum of our original key is. So let's add a printf with %d in the format string and the sum as the parameter. Now we can compile it and execute it with the original key. So here's the sum of all character values for this key. Let's go to the code again and change the key check. Remove the string compare and replace it with the check that the sum has to be that number. Remove the debug printf and try it. So here it says that it's a wrong key and here it says that it is a correct key. Now try strings and you will not find this key anymore. But how can we crack this now? Let's open it with Redare 2, analyze all, seek to the main function and print a disassembly. So let's look for the success or fail message. Here it is. And then we can check where the branches are coming from to find the check if the license was correct or not. Okay, so this compare and jump decides if we print access granted or if we follow it wrong. You can also see this hex value that is used for the compare. I like to use Python to convert between hex and decimal, so that's exactly what we have in our C code. So open the file again in debug mode and add a wrong license key. If we start the program, it says it's wrong. Great. Now let's set a breakpoint with db at this one compare and reopen the file in debug mode. Now dc to continue. Now we hit the breakpoint. With the R, you can see that RIP is at the jump. With dr RIP equals to, we can set the RIP address we want to execute next. And obviously we want to print the success. So we have cracked it again. Okay, so we have found out that if you can find this one compare where it decides if you have a valid license or not, you can simply bypass it. But we are hackers, we love challenges, and patching a jump is just boring. So let's write a Keygen. So first we have to reverse the algorithm. I will open the source code next to it so we can compare a little bit. I seek to the main function and enter visual mode. Okay, so we already know a little bit about this program from the other video. So here we can see the compare if we supply the license key. Then comes the printf, like in our C code. After this printf, we set sum to 0, and also the for loop is initialized with the index counter I to 0. And you can see that in the assembler code to the left. Two addresses are set to 0 with a move. And the address is calculated with the base pointer address. That's just another fancy register. And then the first variable is at offset minus hex 18. And The other one, well, Radari replaced the number with the name and calls it local24 variable. But behind this name is just another number. Now when we look closely, we find a branch that loops back up. So those blocks here are our for loop. And at the end of the for loop is an add instruction that adds 1 to this local variable that was set to 0 earlier. So that is the increment of I. And this local variable that Radari identified is I. We can rename this variable with AFVN, the previous name locale24, and I. In this block we have a string len call. And afterwards we compare two registers, and it either continues with this main block or it leaves. So this is the for loop condition here. Now comes an ugly part if you have never seen this before, but if you practiced it, it's easy to see. Don't worry if you get lost for the next minute. This just requires some practice. So first, it loads a value from an address, which Radari assigned a name to. This name came up before near the string len. And if you compare these two assembler blocks, they are a bit similar. You can see that it adds 8 to the loaded value. So usually that means the value that was loaded is an address, because we have 64-bit and we often divide memory in 8-byte chunks. Imagine an array in memory. It might use multiple 8-byte chunks. The first chunk, which is the first value in the array, is simply there where the address points to. This means that if you want to get a second value in the array, you have to add 8 to the address. Now it points to the second array entry. So this argv1, remember we start counting at 0, so argv0 would be the first array entry. Argv is basically a variable that contains the address with points to an array in memory, and this address is loaded into RAX. And then we add 8 to it to move it to the second entry in that array. Now the second entry is another address which points to a string. In our assembly code we can see that the address of the string is loaded from the location RAX is pointing to. Remember that the brackets around the register means that the register contains an address and we access the value that is stored at this address. Okay, so RDX down here now has the address where our string begins. Now we know that the next line loads the index counter I into EAX. Each ASCII character is 1 byte big, so similar how we can move an address to point to the next array entry by adding 8, we can move the string point to the next character by adding 1. So when we take the counter I, which might for example have the value 3, and add it to the address that points to the start of the string, it will then point to the third character. Now next we load 1 byte from the current address in RIX. This is the value of this particular character. And we add this value in EAX to a local variable at offset minus hex 18, which we earlier set to 0. So this is our sum. Well, I know it seems tedious and confusing and a bit crazy, but if you do this a couple of times and also debug this step by step with GDB and look at your registers in each step and inspect the memory addresses, it becomes clear. So now we know that this is a loop and that goes over each character of the string and adds the character value to a variable. Now when the string len compare branch goes the other way, we'll leave the loop and the sum is compared to hex 394. Cool. If your brain turned off during the previous part, turn it on again. Let's do this again, but this time you can ignore most of the stuff and work backwards with educated guesses. So you see that this address gets compared with a certain value. So look where this value came from. So it has to do something with this add. Now you can reload this binary in debug mode with OOD. I will use ABCD as an example key. Press P to display the addresses and place a breakpoint here. Then use V exclamation mark to switch to a more fancier mode. And then execute it. Now always continue with :DZ and look at the register RIX that gets added. So in the first loop it's hex 41. If you know your ASCII table, you know that this is a capital A. You can also use Python as a handy tool to convert back and forth. And next time it's hex 42. That is a capital B. And then it's hex 43. So clearly it just iterates over the supplied string. See, now you know what happens without having to read assembler line by line. Let's recreate this in Python. Let's write a function called checkKey. It takes a key as a parameter. Now we define a character sum and set it to 0. Then we loop over all characters with for C in key. And then we add the ASCII value to the sum with ORD of C. Then we print the current key and its sum. And we return the sum. Now let's do some example keys. With YY you can copy a line, and with P you can paste it again. I deliberately use ABCD because their numerical values always increases by 1. Cool. You can see how the sum is always 1 bigger than the previous one. Now let's use a very naive randomized Keygen to try different keys until we find one. This can be obviously made much more intelligently because of the linear behavior of this function, but it will still look cool. So import random module and create an endless loop. Our key starts with an empty string. Then we select a random character from an alphabet with random choice and append it to the key. Now we check this key. If this key sum is already too big, we reset the key and start fresh. And if we hit the correct value, we print that key. I will modify the print and check key function to make it a bit more cooler. Now save it and run. Oops, something is wrong. I had to compare the wrong way. We obviously have to reset the key when it's already too big. Okay, now, damn, that's fast. Even though it's very bad algorithm, we quickly find many keys. Let's see if they work. Oh yes, they work. That's cool, huh? So we have learned now that we can hide license keys by using an algorithm to verify if a key is valid. This whole algorithm becomes useless when we find the assembler code that decides if it was valid or not. In our case, it's a simple compare jump that we can patch. Obviously, you can make that a bit more complex, for example, doing a license check in different places, but generally this is how you can defeat it. Now, if we like a challenge, or we don't want to patch a binary, because whatever, there are many reasons why you might want a valid key, we can use static analysis and reverse engineer the license check algorithm and write a Keygen to generate valid keys. Obviously, this algorithm also can become very complex, but generally, if you put a lot of work in it, you can figure it out. Now, you tell that your manager, but he's a smartass and tells you, then you should stop people from being able to reverse engineer the binary. Then you drag yourself back to the desk and you come up with a new creative way how to stop somebody from debugging and reversing it.